For Lab 2, we're going to be doing conversions. We'll be doing some conversions from metric to metric, others from metric to American, and back again. So what we're going to look at first is some examples of what conversions are and the way we approach conversions through dimensional analysis. And then we'll get into more lab-specific examples. For Chapter 1, Section B, we're going to look at doing conversions. So what a conversion is, it's the change in the form of a measurement without changing the actual amount. So if you were going to run a 5K, so 5 kilometers, and you wanted to know how many miles that was, you would end up doing a conversion to go from kilometers to miles. Now once you figure out how many miles are in that 5 kilometers, they're still equal to each other. You're not actually changing the amount, you're just changing the units themselves. The numbers may be different, but the distance is still going to be the same. So let's look at how you would complete this conversion. So with conversions, you are going to need a conversion factor. And what a conversion factor is, it's a number used to change from one set of units to another, and it usually involves multiplying or dividing. So in order to go between kilometers and miles, since kilometers is a metric unit and miles is an English unit, we would have to look up a conversion factor. And the factor that I'm going to use is here in yellow. So I have 1 mile is equal to 1.6 kilometers. And how I'm going to use that is I am going to place it next to my original amount. So I'm starting with my 5 kilometers. I'm going to then use my conversion factors, putting the kilometers on the bottom so that they cancel, and leaving my miles on top. And what I'm actually doing here is I'm dividing. I'm taking 5 and dividing it by 1.6 to get a total of 3.1 miles. So 5 kilometers is equal to 3.1 miles. The numbers are different, the units are different, but the actual distance is the same. Let's talk a minute about exact numbers. So that conversion factor that I showed you a moment ago, going from kilometers to miles, that's an exact number. It's a number that contains no uncertainty. It is found by definition. So I found that conversion factor going from kilometers to miles in a table of conversion factors. It was defined that way, so that's how I know it's an exact number. So the takeaway from this is when you're using conversion factors, when you're using exact numbers, they will never determine the number of sig figs. So you're not going to include them when you're trying to figure out how many sig figs should be in your answer. We'll go through some examples applying this so make it a little bit more clear. So here is a conversion factor, an example of one. Now conversion factors are usually written as an equation. So for instance, 1 yard is equal to 3 feet. Now this would be a conversion factor that I would find on a table. So it would be an exact number. So if I were to use this conversion factor to convert from yards to feet, I would not use these numbers in the conversion factor towards my sig figs. Now, since conversion factors are set equal to each other, we can write them in 2 different ways. We can write them as a fraction with the yards on top in this first example here and the feet on bottom. Or we can write them with the feet in the numerator and the yard portion on the bottom. Now this is going to be helpful when we're doing conversions because sometimes we're going to need the feet on the bottom to get units to cancel. Sometimes we might need the yards on the bottom to get units to cancel. There are also multiple conversions for the same relationship. So what I mean by that is sometimes you might find more than one conversion factor that works. For instance, if you needed to convert from millimeters to meters, you could use this direct conversion up here. I'm going from millimeters to meters, or this memorized conversion, also going from millimeters to meters. Now notice the numbers in front are different. So I have 1 millimeter in the top is equal to 10 to the negative 3 meters. The bottom conversion factor has 1,000 millimeters equaling 1 meter. It doesn't matter which conversion factor you choose, as long as we are canceling out the units we don't want and keeping the units we do, it will still work out. They are actually the same conversion factor, and that's what this is showing here. That when you put them in fraction form, they are still both going to be equal to 1. So let's start by looking at this conversion. We have 0.75 quarts, and we want it in liters. So in order to do that, this is English to English conversion factor. We're going to have to look up in our table some conversion factors. Now, there can be more than one conversion factor to get you to the right answer. And it doesn't matter which conversion factors you choose, as long as you are canceling out the units you don't want and keeping the units you do. So I've written two different ways, and it depends upon the person which conversion factors they happen to find first. So the first way is going to be 2 steps. So using this way, we're going to go from quarts to gallons first, using this conversion factor here. Once we're in gallons, we'll then get to liters by using this conversion factor. 1 gallon is equal to 3.78 liters. So it's a 2-step conversion. Now, if you were lucky enough to find this conversion factor here, 1 quart is equal to 0.946 liters, you could have changed that to just a 1-step conversion, because this conversion factor will go directly from quarts to liters, and you won't need a second conversion factor to continue. So what I'm going to show is the 2-step method, just so you can see how things are canceling in a multi-step conversion problem. So you always start with what's given in the problem. So since the problem is starting with 0.75 quarts, that's how you're going to start your railroad tracks, is with that 0.75 quarts in the numerator. You're then going to figure out which of the 2 conversion factors you need to use first. Now, you're trying to get rid of the quarts, so you're going to want to pick the conversion factor that has quarts in it. So that's why I chose to use the 1 gallon is equal to 4 quarts conversion factor. Now, since it's set equal to each other, remember, we can write that conversion factor in 2 ways. We can write it with the gallons in the numerator or with the quarts in the numerator. We chose to put gallons in the numerator because that's the unit we want to keep, and we put quarts in the denominator so that quarts and quarts cancel, because they're on opposite sides of that horizontal line. So by putting the 4 quarts in the denominator, we have canceled out the quarts units, and if we were to stop there, our answer would be in gallons. We don't want our answer in gallons though, so we're going to continue on using the second conversion factor, where 1 gallon is equal to 3.78 liters. When we're using that conversion factor, we're going to put gallons on the bottom in the denominator so that the gallons now cancel. So now I've canceled all the units. My answer, once I do my multiplication and division, will now be in liters. Now remember, these vertical lines are multiplication signs, so I'm multiplying across. So I'm going to take 0.75 times 1 times 3.78. I am then going to divide it by whatever's in the denominator. So in this case, 4 times 1. The answer that comes out on my calculator is 0.70867 liters. But remember, we still need to check significant figures. We didn't learn those for no reason. We learned them for problems such as this. So, how do you determine significant figures? Remember, we do not use the conversion factors in our determination of sig figs. So we're just going to use the original number in the question, the 0.75. There are 2 sig figs in 0.75, so that means I should have 2 sig figs in my answer. Since I'm multiplying and dividing, remember we're using significant figures as a whole, so that's why I'm counting total sig figs and not just after the decimal, which I would do that if it was addition or subtraction. So 2 sig figs, that means the 7 and the 0 are the 2 I want. I look to the number next to it. That 0 is going to become a 1 for my final answer of 0.71 meters. So here's just a list of steps for dimensional analysis. All dimensional analysis is a big word for conversions. So the first thing you want to do when approaching a conversion problem is figure out what are the given units, what are the desired units. What type of units am I looking for? Am I doing English to English? Am I doing a metric to metric? And we'll talk about that when we do problems on the board. Or am I doing English to metric? This is just going to help you figure out where on your conversion factor sheet to go, where to look. It's going to narrow down the area of that sheet to look in for the correct conversion factors. We're still going to approach all these problems in a similar fashion. Next, write down the relationships needed. So what conversion factors are going to help you get from one to another? Okay, so write those down off to the side so that you have them ready and can put them into your railroad tracks as you go. Make sure that you are setting it up so that units will cancel out that you don't want and units you want to keep will stay. Last but not least, multiply the numbers and divide to get the correct answer. So this video is to help you in completing Lab 2, the metric and American conversions for the pre-lab portion. So the lab portion, how to collect the data and fill out the lab portion of this lab has been posted in a different video. So this is just for the pre-lab. I'm going to focus on the conversion part of this lab. So looking at the first question of the pre-lab, we have a 50 milliliter beaker has a mass of 42.503 grams. Make the following conversions and show your work. All right, so what I want to point out in this first question is a lot of students find it confusing because there's 2 different numbers present in the question. So this 50 milliliters that's written, that is just the size of the flask, the size of the beaker. Okay, we're not going to be using that number at all to do conversions with. So you can ignore that number. It's just telling you what size beaker has a mass of 42.503 grams. So this number, the mass, we're going to be taking that and we're going to convert that number. So we're going to take 42.503 grams and we're first going to convert it into kilograms. Now to do that, there's 2 different ways to do it. One is by looking at the conversion factor sheet for metric to metric conversions. And so the reason I know it's metric to metric, because that's the first step, right, is figuring out if it's metric to metric or if it's English to metric. You look for what's in common. So here I have G for grams, and then I have kg again for kilograms. So GG, that means it's metric to metric. If there were no letters in common, it would have been English to metric. So since it's metric to metric, I can use a shortcut, this KHD space DCM. And what these are symbols for the prefixes of the metric system. So we have kilo, hecta, deca, blank, deci, centi, milli. So when we use this shortcut way, this blank spot
that is where the unit of measurement that we're using goes. So if we're talking about volume, an L would go there for liters. If we're talking about time, an S would go there for seconds. But in this case, the letter we said we had in common was G for grams. So we're talking about mass, so a G for grams is going to go in that base. Now we're starting at the G because that's what the original number given to us was in, 42.503 grams. And we want to go to the K. So we want to go over here to where the K is. So start at the G, and then to get to the K, we're going to move that decimal 1, 2, 3 times to the left. We're going to do the same thing to this number. Starting at the decimal, which is between the 2 and the 5, we're going to move it 3 times to the left. So 1, 2, 3. So this is where our new decimal is, now that it's in kilograms. So what's going to go in that empty space? A 0. So 42.503 grams is going to be 0.042503 kilograms. So this would be your answer in kilograms. Now notice I kept all of the digits. Why did I do that? Because you need to check significant figures. So in the original number, 42.503, all of those digits are significant. 4, 2, and 5 are all non-zero numbers, so they count. That 0 counts because it's between two non-zero numbers and because there's a decimal point. Okay, so all 5 of those are significant. So since we have 5 significant figures in the original number, our conversion number answer will have 5 significant figures. So that means when you work through the rest of these problems for number 1, every one of these answers should have 5 significant figures. Okay, so you're going to go through now and change 42.503 grams into pounds, then into tons, then into decigrams. Right? Same thing goes for number 2 here. So once again, it gives us two numbers, 10 milliliters and 7.12 inches. That 10 milliliters, it's just telling us what size of graduated cylinder is that height. So we're not converting that 10. It's the 7.12. That's the number we're going to start with to convert. So let me do this height in centimeters to show you an English to metric one quickly. So you're going to take that 7.12 inches. For this first one, you're going to convert it to meters. The second one has you convert it to centimeters, and that's the one I'm going to work on now. So I'm going to write it inches to centimeters. Now in this case, it's English to metric because there's no letter in common. So with English to metric, you need a conversion factor. And this would be one of the conversion factors you would find on your conversion factor sheet. Okay, so it's not something I expect you to memorize, it's something you'd have to look for on your conversion factor sheet. So to convert this, since it's English to metric, we can't just move the decimal point. We have to do what I call railroad tracks. So you're going to take the original number, always start with the number given, which was the 7.12. Don't forget your units. And I'm going to make a little railroad track here. Now what's going to go in this empty spot is this conversion factor. And conversion factors can be written two ways. So I can write this as a fraction with the centimeters on top, or I can write it with the inches on top. They mean the same thing. So I have to figure out which one of these two ways is going to work to put here. So imagine picking these up and putting them in this empty space. Now the key is that since inches is in the numerator here, you want inches to be down here in the denominator so that they're on opposite sides of this horizontal line so that they cancel. So the one that's going to work out of these two is going to be this guy here, because you have the inches in the denominator So you can put that down here so that the inches cancel, and then the centimeters in the numerator up top here. That way, inches have canceled and centimeters will be your answer. So to solve, remember, as you go across, these vertical lines are multiplication signs. So to solve, you will take 7.12 multiplied by 2.54. And since there's just a 1 in the denominator, you're just dividing by 1. When you enter that into your calculator, make sure that you are using significant figures. So you have to look to the original number, that 7.12, and figure out how many significant figures are in that number. They're all non-zero, so it's going to be 3 sig figs. So whatever my answer is, I want to stop at 3 sig figs. So my calculator shows this number here. If you put that number in this blank for height in centimeters, it is incorrect because it does not have the correct number of sig figs. Remember, we want to stop at 3. So you're going to go 1, 2, 3. So you want to stop one spot after the decimal point. Always look to the number next to it. If it's a 5 or higher, you're going to round up. So in this case, it's going to be 18.1 centimeters. So that is the correct answer to place in the height in centimeters column. So every answer under number 2 should have 3 significant figures. All right, let's look at the last one now. So you may have seen an example of this one in the lab video if you've watched it yet, the lab data collection video. So this one's a little different because we're using a % error calculation. So the key here is to read this word problem and figure out what is the accepted value and what is the experimental value. And then you just plug in the appropriate numbers. So the accepted value, that is going to be the true value, the correct value, the accurate value. So read the word problem and figure out which one of those numbers is the true, accurate, accepted, measured value. The experimental value, that's usually the guess. What the student guessed, what they thought, what the student came up with, so not the true value. So you're going to figure out which is which and then plug those numbers in. This is absolute value sign, so make sure that if you do get a negative number that you change it to a positive. That's what absolute value means. It means positive. So you'll subtract the accepted from the experimental, make it a positive, and then divide it by the accepted. Don't forget to multiply by 100 so that you get a %. That's how you get the %, is by multiplying by 100. I hope this helped you work through the pre-lab for lab 2. Let me know if you have any other questions. Thanks.